All right, got the live stream up and running.
Okay. Should I go ahead and get started?
Sounds good.
Okay. Thank you everyone for joining us, EPSP Connects today for a science talk, which will be given by Kristin Sweeney. Before we get started, I just want to invite everyone to stay with us into the upcoming year in January, as we'll continue with our webinars. We'll be taking a break in December in order to accommodate AGU, the AGU fall meeting. Okay. Jimmy Geilinger will be partnering up with me to co-host today's talk, and he'll be helping field questions in the chat at the end. Okay. So I'd like to thank Kristin Sweeney for accepting the invitation to talk today. She is an assistant professor in the Department of Environmental Studies at University of Portland, and her talk today is entitled Landscapes on the Fringe, from Volcanoes to Rocky Coasts, and it'll be discussing, I believe, 400 years of monitoring at Mt St Helens, and the role of volcanic debris avalanches in landscape evolution. So without further ado, Kristin, you can take it away.
Great, thanks, Risa. So I've actually changed my talk. So apologies to those of you who came for the Rocky Coast part. It turned out that I had a lot more than I thought I did to say about volcanoes. So this talk is actually all about volcanoes. And so the new title of the talk is Volcanic Debris Avalanches in a Landscape Context. And this is based on some new literature review and global sort of survey data that I've been doing in preparation to submit a paper on this topic to Bulletin of Volcanology, as well as kind of summarizing a lot of the really good work that's been done at Mt St Helens since the eruption, which was now about 42 years ago, coming up on 42 years. So let's make sure I can advance my slides here. So I'll give you first a little overview of where we're going to go. So first, as always, I'd like to talk a little bit about volcano geomorphology, which I still think is a little bit of a niche field, and hopefully convince all of you that it's something that as a community we should be turning more of our attention to. So first of all, volcanoes give us the opportunity to measure initial landscape conditions, so pre-erosion conditions. And then the geomorphic response of landscapes to volcanic eruptions is incredibly important for hazards and long-term management of landscapes. I'll then talk about insights from Mt St Helens. I'll discuss past monitoring of both channel cross sections and sediment yield from rivers draining the mountain. I'll then share some new results which were published in 2020 in a scientific investigation reports using air photos to develop new post-eruption topography. And then I'll share some speculations I have about the role of eruptive topography in channel network development. We'll then zoom out and talk about global implications for volcanic debris avalanche morphology and evolution. So talking about the role of topographic confinement in these events, potential role of climate, and then I'll take you through some case studies. So basically just looking at some cool DEMs that I've been mapping up in my spare time. Before I get into this, this is work that's based on the mentorship and support of many different people throughout my career. So in particular, Steve Titus, my undergrad advisor at Carleton College, Josh Roaring, my PhD advisor, and then Jim O'Connor, John Major, and Gordon Grant, who have been instrumental in providing mentorship, guidance, and some really pointed reviews of my work over the last, I don't know, I guess decade, the last little while. In addition, I also wanted to acknowledge some of my contemporaries in this field, Natalia Deline, who's now at the Hawaii Volcano Observatory, John Perkins, who has unfortunately moved on to studying landslides, Brendan Murphy, Dan O'Hara, and Adam Mossbrucker. And I also wanted to acknowledge the tireless by generations of USGS scientists that has really enabled us to see the development of Mt St Helens in a way that we haven't been able to at other volcanoes. I'll now talk just a little bit about how I got into this work. So I am from Portland, Oregon, which is situated right here on the border of Oregon and Washington. This is the Pacific Northwest of the United States. And this is just a poster showing the eruptive activity of all of the stratovolcanoes in the Cascades over the last 4,000 years. And you can see there's been a lot of volcanic activity at these charismatic volcanic centers. And so as a youth, I was entranced by volcanoes, as many of us were, and I kind of came into it that way a bit. In addition to these tall, pointy things, there's also a lot of monogenetic volcanism that has occurred recently in Central Oregon, which was where I started my scientific endeavors in this topic. So this is Collier Cone lava flow, this sinuous lava flow that you see here, emanating from Collier Cone, which is a cinder cone. This lava flow has been dated to about 1,600 years old, which should be too young to support surface water. So lava is incredibly porous. And we think that it takes a really long time for it to develop enough, for the infiltration capacity to be reduced enough that we can get surface water in these environments. But if you zoom in to this particular landform, what you'll see is there is actually a fluvial channel that's been incised into the lava flow. And so this work was basically focused on how the heck did that happen? So I did a bunch of modeling and some field work. I'm not going to be talking about that today. Instead, I'll be talking about some work that started with these boxes, which entered my life after my PhD when I was a postdoc. So these are boxes of archival aerial photography of Mt St Helens, starting in 1980 and going through 1996, approximately annual frequency. And basically these were just sitting in a closet at Cascade Volcano Observatory, and the sort of premise of my postdoc was surely we can do something with these air photos. And it turns out indeed that we could. And so I'll tell you a little bit about that work going forward. This has continued to be relevant as the U.S. Forest Service seeks to manage the lake levels at Spirit Lake, which is shown here in a photograph from 1980. So Spirit Lake is a lake to the north side of Mt St Helens. This is Mount Adams in the background. And Spirit Lake, the natural outlet, was dammed by the eruption of 1980. And that damming meant that the lake level started rising, which was going to present a lot of hazards, like downstream hazards. And so a tunnel was dug through the eruptive deposits in order to drain the lake. Over time, that tunnel has degraded, and so the US Forest Service was interested in knowing what other options there might be for managing the lake level, including digging a channel across the surface of the blockage of the lake. And so some of the work we've done recently has been in service to that management question. So why do we care about volcanoes? From a geomorphology perspective, volcanoes or volcanic deposits provide initial conditions for geomorphic evolution. So basically you can take the uneroded volcanic surface, and if you look at a cross section across this, this lava flow, you can see here that there's this really nice flat uneroded surface. There's a channel in the middle. These are lava flow levees on the sides. So these are primary eruptive topography, not post-eruptive modification. And then you can basically just calculate how much volume has been eroded for any given channel cross-section or any given landform. And if you know how old the volcanic deposit is, then you can figure out how much erosion has occurred in that location. And you can do this at a variety of different timescales. So Collier Cone, we're looking at a couple of 1,000 years. You can do it at Mt St Helens, where the North Fork of the Toutle River has eroded through the eruptive deposits on the north side of the volcano very rapidly, as we'll see a little bit later in the talk. And you can also do this in large-scale eruptive deposits like those produced at the Okmok caldera in Alaska. So here we can see this gullying and channel formation happening in this tephra blanket. So you can do a lot of cool things with this, and I'll just cite two examples here. So in 2013, Ferrier and others used this approach to examine the impact of mean rainfall on channel incision parameters, specifically the stream power constant K. In 2014, Luke McGuire and others looked at how different geomorphic process parameters might control cinder cone morphology. So they were proposing that basically you could use the morphology of cinder cones to back out past climate conditions. And they could do this because cinder cones have a very regular geometry. The geomorphic response of landscapes to eruption also drives hazards and human scale management. This is on the left here is a sediment-laden flow coming out of Redoubt in Alaska in 2009. And so these sort of downstream flooding sedimentation hazards are incredibly common at volcanoes. This is an image of the Spirit Lake Tunnel at Mt St Helens, which, as I mentioned, had to be dug to drain the lake or to maintain the lake levels so that there weren't downstream hazards. And another management issue that's happening at Mt St Helens and continues to be an issue is the sediment retention structure, which is at the downstream end of the North Fork of the Toutle River. And so you can see here that this sediment structure is, or this dam is retaining a ton of sediment that's coming off of the mountain. And over time, this has had to be dredged, the level of the dam has had to be raised. And so it's really important that we understand the erosive processes that are happening upstream that then produce sediment yield at the downstream end and impact these management decisions. All right, so we've talked a little bit about why we should care about volcanoes in a geomorphic context. And so now we'll move on to discussing insights from monitoring at Mt St Helens. So I'll start by discussing just the general 1980 eruption and deposit. So in 1980, Mt St Helens erupted laterally to the north, initially forming what they call the blast pyroclastic density current, which is shown here in gray. So that basically swept the vegetation, in some cases entirely removing it, in other cases just downing it in the area that's outlined by this gray polygon. The collapse of the edifice formed a volcanic debris avalanche shown here in the sort of burnt orange color, which hit Johnston Ridge, which is across from Mt St Helens, and then swept down the North Fork of the Toutle River, subsequently turning into a lahar. And those lahars actually went all the way into the Columbia. The lahars are shown here in brown. Lahars also impacted the South Fork of the Toutle River, Swift Creek, Pine Creek, and the Muddy River here. There were also pyroclastic flow deposits that, as is pretty typical for this type of eruption, were fairly confined to the sort of area right around the edifice. Mt St Helens is one of the most well-documented eruptions, both the actual eruption and then the post-eruption evolution of the landscape and the volcanic system. These are two images of USGS scientists collecting geomorphic data at Mt St Helens. So up here on the top is someone taking a survey of a channel cross-section. Some of that data we'll look at in a few minutes. And then here's someone taking suspended sediment measurements at the North Fork of the Toutle River during a high flow event. Mt St Helens also has a ton of other monitoring stations that are not geomorphically related. So the blue stars here are showing seismometers and the black triangles are showing GPS. And then all of the little circles are detected earthquakes. And so we can see that these, I might have had that backwards. Actually can't remember now if it's stars. Anyway, seismometers and GPS. So the density of monitoring at Mt St Helens is really incredible and allows us to gain insight into all kinds of things about how the magmatic and geomorphic systems are working. Before we get into the details of Mt St Helens, I wanted to talk a little bit about the different types of landscape response to explosive volcanic eruptions. So this is a figure taken from Pearson and Major 2013. And so here we're looking at a few different effects that can happen from eruptions. So mass movements can block tributaries and cause lakes to form. We'll see several of these in this talk. These lakes can be temporary and then they can be breached, or they can kind of become more permanent parts of the landscape. One of the first things that happens after an eruption is there's rapid erosion of the fresh unconsolidated volcanic deposits, particularly on the hill slopes, which then get deposited into the channels, which typically cause the channels to erode, right? So they're responding to a really high increase in sediment load. Ultimately, in bigger mass movements, so very large lahars or volcanic debris avalanches, you'll end up developing a completely new channel network that will incise into the deposit. And so we'll also see that happening at Mt St Helens. So now we're going to talk about methods that have been used to measure post-eruption landscape change at Mt St Helens. So there have been hill slope erosion plots as done by Collins and Dunn in 1986. There's been extensive monitoring of the sediment loads in rivers that drain the mountain. There's been repeat surveys of channel cross sections going back to 1981-82. And then more recently, we've produced digital terrain models, both from LiDAR and then also digital surface models from photogrammetry, so both traditional photogrammetry and then also structure from motion, which is where my work comes into this project. The figure here is showing the 2009 LiDAR, and then these black lines are schematics of cross sections along the channel. There's actually a lot more cross sections, as I'll show in a future figure. And then this is colored by the geology. So the yellow is the volcanic debris avalanche, the blue is the pyroclastic flows, and then the purple is the blast deposit. So first of all, the hill slope response at Mt St Helens was relatively short-lived. So initially there was overland flow due to reduced infiltration capacity. There was up to 1 meter of tephra deposited on the hill slopes, but that varied by topography. And then those deposits were largely removed in the first 4 years after the eruption. And we can see that in this plot. So on the y-axis, there's a proxy for erosion. And then on the x-axis is time going from 1980 to 1983. And so you can see initially there's a high rate of erosion both in rills and between rills. And then that declines quite rapidly within a year or two. And that's what this looks like in a landscape. This is from Chai 10. And so you can see these really intense gullies forming on the hill slopes. These are trees for scale. So all of these little ephemeral channel networks that form within the tephra that then gets stripped off. The response in the channels really depended on the volcanic disturbance type. So we're going to look at data from a few different channels, and I'll just show you what they look like now on a Google Earth image. This is actually from 2015, I think. So this is the South Fork of the Toutle River. This is the North Fork of the Toutle River, and you can see the upper part of the Toutle River the North Fork Basin is still highly disturbed. So this is the volcanic debris avalanche and pyroclastic flow deposits. And they remain largely unvegetated. And so I like to think of them as kind of just like a pile of sand and gravel, just like sitting up there waiting to be eroded. So this is really the most disturbed catchment on the mountain. So if we look at the sediment yield coming out of these rivers, so we're looking here from 1980 to 2000. There's data later than this as well that I haven't included here. The North Fork of the Toutle is shown here in the dots, and then we'll compare that to the South Fork of the Toutle, which is in the squares, and the Green River, which is in the triangles. And so you can see that the North Fork of the Toutle River had by far the highest sediment yield of any of these basins. And that we think that's because it was the most highly disturbed. And notice here the log scale. So we're talking here orders of magnitude. The South Fork of the Toutle River, which was disturbed by a lahar, also fairly high initially, and then kind of drops off a little bit. The Green River, which was only disturbed by the blast, had a slightly heightened sediment yield, which then decayed really rapidly after the eruption. You can see the drop off right here in the North Fork Toutle River data has to do with the construction of the sediment retention structure. So the gauge is downstream of the sediment retention structure, but reconstructions of that sediment yield suggest that it remained elevated for most of this period. The rejuvenation you see in 1996 is related to a regional flood that happened that year, and we'll talk a little bit about that in future slides. We still see a lot of sediment or really high sediment yields coming out of the North Fork of the Toutle River. This is a picture of the Toutle River which is downstream of the North Fork in December of 2015. And so you can see here the water is incredibly turbid, and a lot of that sediment is coming off of the disturbed area of the North Fork. The hydrologic history has what we've observed is that the hydrologic history has a strong impact on the geomorphic evolution. So there was a lot of, remember there were high sediment yields in the 1980s. Aside from this February 1982 flood, which was partly related to a lake breaching that was dammed by the volcanic debris avalanche. This gray line is a 4-year recurrence interval flood. You can see that the 1980 eruptions, hold on. Can everyone hear me okay? Sorry.
Yes.
Okay, there was a weird mute thing that happened. All right, so you can see that in the 1980s and 1990s, things were fairly, as John Major would say, pedestrian hydrologically. And then we had this big flood in February of 1996, and then another one in 2006 in November, and then another one in December. And so these events really punctuate the geomorphic evolution, as we'll see in the cross-section data going forward. What we'll look at next is some cross-section data from the debris avalanche, from channels on the debris avalanche. So we'll just look at 4 cross-sections. There are many, many more, and they've been published in a digital data set that you can download from the USGS. It's all Excel files, so you can make your own really cool plots. Pretty fun. So the overall observations here were that the greatest channel change occurred in the first 3 to 5 years after the eruption. There was an initial pulse of incision followed by mostly channel widening. In the upper reaches of the North Fork, there was incision that was partly driven by management decisions, including pumping of Spirit Lake over the debris avalanche deposit, which I'll discuss when we get there. The lower reaches of the North Fork experienced aggradation from the pulse of sediment followed by secondary incision. And while lateral adjustments now dominate channel change, that lateral adjustment doesn't occur consistently. So we still are seeing a pretty substantial incision of channels in some places. And as I mentioned, large hydrologic events can still lead to very high erosion rates and sediment yields. So we'll start by looking at the Lewitt Channel, which is in the upper reaches of the North Fork. We'll then look at the Truman Channel, also a tributary to the North Fork, We'll then move a little bit downstream to look at this one, which is sort of situated rather centrally. And then we'll look at a cross-section that's quite a bit downstream, NF350, which experiences that aggradation signal. So what we'll be looking at here, I'll just orient you to these. So all of these graphs are going to look the same. I'll just click through a time series for each cross-section. So the x-axis is going to be distance from the left monument. So imagine you're looking downstream on the channel, and then the y-axis will be the elevation. And then the time or the year is given over here in the legend. So this is what the Lewitt channel looked like in 1981. In 1982, there had been some aggradation and widening. 1983, 1984, substantial incision. 1992, some aggradation, and then 2005, more incision. And remember, this is a period that brackets that 1996 flood. And then in 2007, there was substantial incision as well, related to that 2006 flooding event. So overall, there's been about 20 meters of incision in 25 years at the Lewitt channel, so really high rates of incision. The Truman Channel experienced around 20 or 30 meters of incision that was largely driven by lake pumping. So in 1982, the channel looked like this. And then there was, as to manage the lake level at Spirit Lake, this was prior to the tunnel being constructed, they started pumping lake water over the Debris Avalanche deposit, which caused rapid incision. So this is what the channel looked like a year later in 1983. And then in 1989, you can see that there isn't a ton of change. There's a little bit of sort of readjustment. But the largest amount of incision really occurred as a result of that management decision to pump water over the Debris Avalanche. The North Fork 100 cross-section, which was that one that was kind of right in the middle, has a complex incision history that's punctuated by those storm events. So in 1982, the cross-section looked like this. 1983, 1984, 1985, 1987, you can see that there was a new channel is kind of being incised in the middle. This one is 1990, 1998. So this is that period bracketing the 1996 flood. We kind of remove this, this little thing right here. 2005, there wasn't much change. And then in 2007, we see this incision of an inner channel forming these terraces. So that's related to that 2006 flood. 2013, and then 2017, there was a bank failure that caused widening of the channel here. And then finally, we'll look at the North Fork 350 cross-section, which is substantially downstream of that image that I showed you. And so here, the channel looked like this in 1981. In 1983, there had been substantial aggradation, so about 5 meters or so in the main channel. In 1986, the channel widened considerably, and then in 1998, it started incising a little bit every year. So we kind of had that aggradation and then secondary incision. The cross sections really give us a strong but somewhat granular picture of channel evolution, right? So we have a really clear understanding of what's happening at each of these white lines. So these are all the cross sections that have been monitored at Mt St Helens, shown here in these white lines again over this LiDAR hillshade. And so what I did during my postdoc was to try and use air photos to get a more holistic sense of what was happening with the erosional system or with the sedimentary system over the entire deposit rather than just confined to single cross sections. So what I did was use traditional vertical aerial photos and put them through structure from motion software to generate topography. This is something that's really difficult. I'm sure some of you have done it before. And the reason is that the way that traditional aerial photos are flown is they're flown in parallel lines with pretty low overlap, so like 30% overlap. And this flight pattern causes radial distortion errors to propagate within the program, causing doming. So what that looks like is shown schematically here on the left. So if you take a flight of a flat landscape and you process it through this type of flight pattern, what you'll end up with is something that looks like a dome. And obviously that's not what we want. It causes a lot of like really crazy looking artifacts to pop up in your data. And you can avoid this in new surveys by not flying in parallel lines, right? Those of us who have done structure for motion have had it hammered in like convergent look directions. You have to have the cameras pointing in at each other, not this like straight line business. But you can't really get around it in archival data sets. And so what we did is we used a 2015 georeference survey to create a bunch of ground control points within our photos to try and basically correct this error. And this is work that an undergrad student of mine did a few years ago, where he looked at a lot of photos and tried to find things that were invariant over time. This is one of the best examples. So this is a parking lot. And you can see that it has, this is 1984 on the left and 2015 on the right. And you can see that it has these really nice like geometrical corners and shapes. And so you can, you know, pick those corners and match them from 1984 to 2015. This becomes a lot more difficult when we're in the middle of the volcanic debris avalanche, which is changing so rapidly as we saw in the cross sections. And, you know, is being revegetated, various things are being buried. So yeah, so my student Parker spent his entire summer looking for boulders and logs and other things that we could convince ourselves had not moved over time. And so I'm going to show you the results from doing that. And we're going to be looking at DEMs of difference, which are when you subtract the DEM from 1 year from the DEM of a second year. And all of these have relatively high, or I guess the detection, we can't really detect very fine change. So basically our detection level is based on how good our reconstructions are of and various other things. So this one, for example, our detection level is 4 meters. So any change that was less than 4 meters, we did not detect in this map. And we took a relatively conservative approach because as you'll see, even with these thresholds, you'll still see artifacts in the DODs. So in 1980 and 1981, between those 2 years, the primary thing that we saw was filling of depressions within the volcanic debris avalanche deposit, and then also initiation of the channel network. So blue here is always going to be depositions. So you see these blue blobs. These are all places where there were sort of ponds and lakes within the volcanic debris avalanche deposit. The warm orange colors are going to be erosion. So we see the initial incision of Lewitt Creek and a few other little channel systems throughout. From 1981 to 82, we saw a sharpening of the channel network. So we see incision kind of along the banks of the channel, not as much in the fall leg of the channel. So this really just kind of like establishes the location of different channel forms. From 1982 through 84, this was the period where they were doing that pumping from Spirit Lake. And so you can see there's incredibly high incision in the Truman Channel. That cross section we were looking at is right here. And there's also incision up Lewitt Creek. So, you know, we're dropping the base level that Lewitt Creek is draining to, which potentially causes a propagation of incision upstream into Lewitt Creek as well. From 1987 through 1996, so this change is primarily driven by the 1996 flood. We see widespread channel widening, but then also incision, particularly at this area called Carbonate Springs. This is a set of springs that are located right here. And you can see in this image the artifacts that tend to pop up. So all of this, this sort of stuff that's labeled erosion and deposition that's happening over here on Johnston Ridge, that's not real. So one of the things that I was really excited about with this data was the ability to ask the question of how eruptive topography potentially influenced the shape and location of the new channel network that developed after the eruption. And so we can think of the eruptive deposits as having kind of two scales of topography. So we have sort of the large scale, like, is it overall tilted away from the crater or towards the crater, you know, like that type of scale. And then we can also think about a smaller scale. And as we'll see, one of the things that really characterizes the volcanic debris avalanche deposits is hummocks. So it has most volcanic debris avalanches have very hummocky topography. And so I was really curious about what role those hummocks might play in potentially steering the future channel network. So first we'll look at the sort of larger scale topography. So here, this is looking at cross sections from A to A prime. So going from the crater northward, and then two that go from Spirit Lake downstream. And so you can see overall that the deposits slope downwards from the crater, as you would expect, and that the Truman Channel is located at the low point of that cross section. Similarly, if we're looking in the other direction, so here we have E to C prime, C prime is here, or sorry, C is here, C prime is here, and then B to B prime. The main channels, so Lewitt Creek and the North Fork of the Toutle River, are located at the low spot in the topography, as you would expect. So it seems like the big scale topography of the eruptive deposits really has a strong influence on where the channels end up. So now we'll look at some examples of potential channel steering. So this is a zoom in of that image I showed earlier. Blue is pyroclastic flow, yellow is volcanic debris avalanche, and then the pink is the blast deposit. So we'll first zoom in right here. And on the left here, we're looking at 1980 topography. And so this lump and this lump, those are both hummocks. And we can see then in 1981 that the channel that initiates flows right in between those hummocks and through this depression that's right here. And if we go back, we can see that the channel is still located there, right? So these two hummocks in particular seem to have had an influence on where that particular channel formed. In contrast, we'll now look at a place where the hummock really didn't matter. And we'll zoom in right here. And at first you might look at this and think there's no hummock there, but this little blob right there is a former hummock. And in 1980, it looked like this. So this is that same landform right here. There's a big lake. And you can see in 1981, the channel kind of steered around it. This is not the best part of the DEM, so it's a little grainy, but there's a channel form right here. And then in 1982, we see the channel is still there, but that hummock has started shrinking. So the edges of it have started kind of getting eaten away. And then in 1984, after that pumping event, it's been totally obliterated, right? So the channel just like cut right through it. And so this is a case in which the hummock just like didn't have any effect on where the channel went. All right, so some take-home messages from Mt St Helens. First of all, like many other explosive eruptions, there was an initial pulse of sedimentation that then decreased rapidly, but remained elevated and has continued to remain elevated to this day. The sediment loads in channels that draining the volcanic debris avalanche remain very high, and we think that's due to persistent channel mobility that we observe on the debris avalanche deposit. And finally, or not finally, but the system appears to be transport limited. So we really need these large hydrologic events to drive any sort of large erosion rate. But when we do get it, in general, not always, but sometimes, we do still see a really strong, we see a strong sedimentary response. And then finally, it appears that the channel network geometry is primarily driven by larger scale topography and that there's limited steering by hummocks. There are some cases, but you kind of have to look pretty hard. I looked pretty hard because I was like really excited by this idea and then turned out like not to really be a thing. Okay, cool. So we've talked now about Mt St Helens, and now I'm going to zoom way out, both in terms of space and time, and talk about volcanic debris avalanches more generally, and some thoughts about morphology and evolution. So volcanic debris avalanches, which are I'll talk a little bit more specifically about what they are, but they're basically the collapse of volcanic edifices, have been widely identified throughout the world. So this is a map from Dufresne et al. In 2021, showing all of the events that have been identified. The circles are scaled to the number of events for a particular region. So for example, 155 events have been identified here in, I believe this is for Japan, 69 for Indonesia, et cetera. And so they've been widely identified, but they're really under monitored. And in the literature, a lot of the work has been of the flavor of, we found another one, and here are some implications for hazards, and less of the, how does this event or these events impact long-term landscape evolution or impact the landscape evolution of this particular area? And that's kind of the angle that I'm more interested in. So what is a volcanic debris avalanche? I really like this definition from Bernard et al. In 2021, which is that the initiation phase can be described as a translation, rapid and mostly horizontal, of one or more portions composed of multiple volcanic units over a slide surface produced by a failure in the volcanic edifice. And it's shown visually here on the left, where we have the volcanic edifice, and then essentially like a big chunk of it slides off and rapidly translates down the mountain, often in its translation forming these hummocks, which are characteristic of volcanic debris avalanche deposits. So the questions that I am interested in are, first of all, what factors control the topography of that primary eruptive deposit? So, and I'll be calling them VDADs, which is the sort of the abbreviation in the literature. Then what controls the shape and course of new drainage networks on VDADs? And what controls the preservation of VDADs in the sedimentary and topographic record? Before I get there, though, I wanted to give you a little more information about VDADs. This is an image of the bulge at Mt St Helens, which was prior to the 1980 eruption. This image was taken April 27th in 1980. You can see, like, this is a pretty scary looking thing to have growing on the side of a volcano. And it was growing incredibly rapidly right before the eruption that ultimately collapsed this side of the volcano. So they can have magmatic and non-magmatic origins. So Mt St Helens is an example of a magmatic VDAD or VDA, because after the rise of the magma was causing the bulge, and after the failure of that, there was a magmatic eruption that was associated with the volcanic debris avalanche. However, there's a lot of evidence in the literature that you can have these events happen without actually having any magmatic activity. This is an example from Van Wyk de Vries and others in 2011. And this is the sort of gravitational spreading argument, where you basically form a really heavy stack of volcanic layers on top of a weak basement. So they typically talk about like lake basin deposits or other types of weak things. And so once you put enough load onto those deposits, they start to flow out the sides. And that flow then causes instability in the overlying volcanic debris avalanche, in the overlying volcano, which then causes a volcanic debris avalanche. And you can often see sometimes in these deposits that there's some like weird lake deposit stuff that's kind of like squeezed out the front, and that's used as evidence that they might have indeed been triggered by this gravitational spreading mechanism. So one of the things that's really characteristic of these events is the hummocky topography. And so here are a couple examples. On the left, this is Augustine in Alaska. I believe this is the West Island debris avalanche. On the right, this is Mt St Helens. Again, we can see all of these hummocks. And then sometimes these hummocks are incredibly large. This is Yocotitlán in Mexico, and you can see these hills are hummocks. You can see trees and houses in the foreground for scale. So these can be very large parts of the landscape, the hummocks themselves. And in the past, prior to the Mt St Helens eruption, many of them were misinterpreted as volcanic centers in their own right? So, oh, it looks like a cinder cone, or it looks like a lava butte, or whatever. Sometimes they were interpreted as glacial or other types of landslides. But once the Mt St Helens eruption happened and produced this really characteristically hummocky deposit, there was sort of an aha moment that happened in the volcanology community, and suddenly it was clear, like, oh, these actually happen as stratovolcanoes all over the world. It appears from the literature pretty clearly that topographic confinement of volcanic debris avalanches affects their morphology. On the left, this is Tetavicia in Bolivia, and on the right, this is Huayaco in Chile. I have a really hard time with that. And both of these are volcanic debris avalanches that ran up against topographic obstacles. And I really like this example on the left because you can see how the hummocks against this topographic obstacle, at least on this side, really piled up against each other. And so they got a lot closer together versus being more spread apart, which has kind of interesting implications about what then happens in terms of the erosion of these deposits, right? How they might steer channels. And, you know, there's, I think, a really strong potential for climate to play a role in post-eruption evolution, right? So fundamentally, even we need some sort of hydrologic engine to drive the erosion of these deposits. And if that's, and sort of the details of that engine probably have a lot of impact on how the deposits evolve over time. So now I'm going to take you through a few case studies of places that I've looked at the topography and thought about it a little bit. And I'll just plot them on this very schematic climate graph of temperature and precipitation. So we'll start off looking at Socampa, which is in the border of Chile and Argentina in the Atacama. It's hyper-arid, high elevation. We'll look at Bandai, which is in Japan, about 1.4 meters of rain per year, around 10 degrees Celsius average temperature. We'll look at Shasta, which is a little bit drier, but a little bit warmer. And then at Iriga, which is in the Philippines and is in a tropical climate, so quite wet and very warm. And then we'll round out our 5 examples by looking at Augustine, which is polar, is in Alaska. So we'll start by looking at Socampa, which is in the Atacama Desert. And so this event occurred, it's right, the deposit is right here. It came out of this, the edifice of the volcano is right here, and then it flowed kind of this direction. And you can see the little lobe of it kind of squeezed out through here. So this occurred about 7,000 years ago. It's 26 cubic kilometers in volume and moved about 40 kilometers laterally. So these are incredibly huge events relative to other landslides and can travel very, very far. And then you can see it's kind of partly confined at the distal end. This is SRTM data, and one of the real limitations for me on this project has been that a lot of the world doesn't have high resolution topography data, and so it's really hard to see like channel initiation into these deposits at this scale. You can see that there are some channel networks along the edge here, but I have been unable to convince myself that there are any channels incised in this deposit. And I would suggest that this is potentially largely because of the climate, right? So we're in a hyper-arid, high elevation setting, and so the likelihood of there being enough liquid water to incise a deposit of this scale is probably quite low. We'll next move on to talking about Bandai in Japan, which erupted from Mount Bandai here in, there's the deposit in 1888. And it went this direction. It was quite confined, but you can see that it blocked several of the drainages and formed a series of new lakes. Some of these lakes are now, the levels are now managed with dams. So there's a dam right here under my cursor. And this is this was the genesis of the idea of a Bandai type eruption, where you have a debris avalanche that's then associated only with a phreatic explosion. And again, there's not a ton of, I was unable to see a ton of channels developed in this one, but yeah, this work is ongoing. So yeah, maybe I'll find some. Number 3 is Shasta, which is one of my favorites. One of the largest quaternary landslides ever recorded, covers an area of 675 square kilometers. And it's at least 45 cubic kilometers in volume, as estimated by Crandall and others in 1989. Happened about 300 to 380,000 years ago. Like in many other places, the hummocks are block facies, which means that if you look like inside a hummock, it tends to be an unbroken chunk of the ancestral edifice. And then between the hummocks are matrix facies. At Mt St Helens, even though the hummocks we think are block facies. We haven't seen really large clasts. So I think the largest clast seen in one of the hummocks in Mt St Helens is like 1 meter, but they can be kind of more like tens of meters in some of these other events. So that sedimentary or sedimentological difference might have some effect in how these events unfold. And I think in this case that there's evidence of channel steering within this deposit. So this is now the deposit overlain with the named streams in the area. The thick blue line in the middle is the Shasta River. And if we zoom in even further on that, what you can see is that the Shasta River does appear to be steered pretty substantially by the location of these hummocks. So you can see in particular, like right here, it goes right between the hummocks, and right here, it kind of takes this circuitous route through the hummocks. It goes between the hummocks again here. And I think this really has to do with the, the surface itself is pretty low relief, and then the hummocks are relatively high relief. Iriga is another example. So there are actually 2 debris avalanches in this image. There's one that's undated but older to the southwest, and you can actually kind of see some channels that sort of drain into that deposit. And then there's one that erupted that was in place to the southeast here and blocked all of these drainages and formed Lake Boogie. It also has a really nice collapse crater, very classic horseshoe shape. And then finally, we have Augustine in Alaska, which has 3 volcanic debris avalanche deposits. So the West Island deposit, which is here, the Rocky Point deposit, which is here, and then the Burr Point deposit, which is here. And as you can see, these are much less aerially extensive than the other examples that I showed. And part of that is because Augustine is located, I didn't label it here, but it's located right up here in Alaska. And as such, it's subject to tsunamis. And so a lot of the volcanic debris avalanches and other deposits on Augustine have been removed by tsunami activity. And furthermore, it appears that a lot of them have just gone into the ocean. So there's been bathymetry studies done at Augustine where you can see that there's hummocky topography below the surface of the ocean as well. And then also there's a very high rate of magmatic flux. So the edifice is rebuilt every 100 to 150 years, which then means that the deposits are often covered by subsequent volcanic activity. So I think some quick take homes from the global stuff. So I am pretty convinced that the confinement of these events drives the transport capacity of the network that forms and the deposit preservation. So if we compare what the deposit at Shasta looks like, so this deposit is 300,000 years old, to the deposit at Mt St Helens, which is only 40 and a little bit, you can see that there's been such substantial erosion of Mt St Helens compared to the Shasta deposit, which is relatively intact. And what I'd like to suggest is that this is because the volcanic debris avalanche at Mt St Helens came out of the crater, hit Johnston Ridge, and then took a left turn down the North Fork of the Toutle River and was confined to that valley. And so the water that's flowing through this system is also confined to that valley and hence has the capacity to really rapidly in size versus a place like Shasta where either the debris avalanche itself was relatively low relief or it was placed into a basin that was relatively low relief. And so you get this very gently sloping surface that doesn't produce the same confinement of both the deposit and the water. The role of climate in these processes is challenging to isolate, just like it is in every other geomorphic problem. So this is just an example of doing this in volcanoes from Ann Jefferson's work. And so what they tried to do was they were looking at island arc volcanoes, and they were classifying them as weakly dissected by channels, substantially dissected, or raised. So basically flattened. And we're looking here at a plot of representative volcano age and representative precipitation rate. And so one hypothesis might be, oh, you have a higher precipitation rate, you'd expect it to be more dissected. And that's not really what we see, right? The dissected volcanoes are kind of all over the precipitation rate, and really it's just a function of age. And I asked Taylor Perrone, who was a co-author on this, about it, and he wrote me in an email that it was a bit of a dog's breakfast. And I think that, you know, picking what you're gonna call the climate variable of relevance is really hard. And then also a lot of these volcanic deposits integrate over a lot of different climate cycles. And so, you know, trying to tie modern climate to the overall evolution of the landform is also quite difficult. And so on that equivocating note, I'm happy to take any questions.
Thank you, Kristin. That was an excellent talk. I learned a lot. I think I guess we need to give some folks a chance to type in questions, please. Here we go. Okay, so Will, that looks like a long question. Just to speed things up, do you want to ask? Can you unmute yourself and ask? Will?
Sure.
Okay.
Yeah. Can you hear me? Awesome. Yeah, so I'm super intrigued by the routing of the channels around the hummocks, both at Mt St Helens and elsewhere. And I'm really just kind of curious if you think that there's like a clear relationship between the scale of the hummocks and the discharge that's necessary to either route the channel around the hummocks or at which the hummocks don't matter. Like, is there sort of a characteristic discharge at which hummocks are important versus not?
Yeah, that's a great question. I think my sense is that more than discharge, it's related to the relief of the channel relative to the relief of the hummock, if that makes sense. So like at Mt St Helens, the hummocks mattered when the channels were initiating and they weren't heavily incised. But once the channels kind of like cut down into the deposit and the hummock was kind of just like, I don't know, like I think of it like cake decoration on top of like this big layer cake. You know, it just like, it didn't matter anymore. Whereas at Shasta, like the relief of the hummocks relative to the relief of the channels is much higher. And I guess when I'm saying relief of the channels, I mean like the height of the channel banks is kind of what I would think about, I guess. But yeah, I'm not sure I would tie it to a specific discharge. I think that would be really like system dependent in terms of like what discharges are, you know, geomorphically effective for a given location.
Okay, any other questions? Thanks, Kristin. We're happy to take any more questions.
I guess, yeah, I'd throw this out here. Was like in terms of these volcanic or these VDADs, is there, it seemed like you were alluding to the fact that there wasn't much of a difference in terms of like the competency, maybe in the different phase sheets of a lot of these things. Could that be like, could there be kind of like some variability in that in terms of controlling their evolution?
Yeah, absolutely. And I think that depends a lot on the event. Like, I think that we haven't seen that effect at Mt St Helens very clearly. I've looked, so I had a student, there's a more detailed version of the geologic map that maps out the different facies of the Debris Avalanche that was made by Harry Klicken. And I had a student a couple terms ago digitize it for me. And we didn't really see any clear link between the channel patterns and the patterns of the primary eruptive deposit. But I also think that that might have to do, like I mentioned, with the sort of like not particularly impressive class size at Mt St Helens compared to other locations where there are actually like really significant chunks, like intact chunks of the volcano that are just kind of like sitting out there. so yeah, I think it has like every theory that we know would suggest that the size and strength to some extent of the material should really matter. And I think the reason we don't see it at Mt St Helens is there's just not enough difference within the deposit to really like have those effects be clear.
I guess I just came up with a question. I guess this probably goes a little bit outside what you were talking about, but for like management purposes, I guess what differences might there be between forms and structures to stability, like much further outside of the perimeter? The perimeter is like you were talking about, you know, like where there's residential areas or, you know, development. Like, are there any particular characteristics of styles that affect stability more than others?
I guess I'm not totally clear on what you're asking. Are you asking like, are there like other mitigation measures that have been put in place downstream of these events to like protect infrastructure, or?
Well, or like, yeah, and I mean, are they different? Like, do they respond differently amongst themselves compared to the events, or like which, you know, the materials involved, or?
Yeah. I mean, I guess so, you know, although these events are like everywhere, there aren't that many that have happened in kind of like modern times that have been managed in that way that you're talking about.
Yeah.
I mean, I think the approach at Mt St Helens has very much been to manage things on the upstream end in terms of both managing the lake level and then managing the sediment flux. So like, you know, the purpose of keeping all of that sediment behind the sediment retention structure is that if that sediment load was going down the Toutle River like every winter, that would produce a lot of flooding hazard for, like, there are communities along the Toutle River that depend on the sediment retention structure to kind of like keep things on the level. And there's also important navigation channels like in the rivers that the Toutle River drains to, so the Columbia, et cetera, and that are economically important and hence like we need to keep sediment out of them. But I think the approach has been much more to manage that sediment kind of like away from the population center and the industry center.
Okay, yeah.
Is what I think you might be talking about, which is close to, like, away from the mountain, what's been happening. So
okay, thanks.
Yeah.
If there are no other questions, Jimmy, you can
I guess, yeah, I have one more too.
Okay.
In terms of, I guess the role like revegetation too of a lot of these deposits, how in terms of like primary succession, all of that, did that kind of play a role in maybe stabilizing some of these landforms and from a hill slope erosion standpoint and hydrology?
Yeah, that's a great question. Yeah, so I think that vegetation, you know, honestly, the revegetation has still been quite slow. If you ever get a chance to go to Mt St Helens, strongly suggested. It still looks like really recent. Like it's very much like it looks like a disturbed landscape. And I think there are kind of like hotspots of revegetation around springs, and then a little bit further downstream from the crater, there's this area where there's a lot of hummocks and closed depressions, and those have been kind of like hotspots of places where like a lot of plants have grown and things like this. I think, you know, that was one thing that I, going into this postdoc, was kind of like hoping / expecting to see was some sort of coevolution of vegetation and the channel system, because that's been observed at other volcanoes, most notably Pinatubo, work that Karen Gran has done, where they've seen vegetation come in and really stabilize the channels, reduce the sediment flux, et cetera. But the situation at Pinatubo is a bit different because it's tropical, for one. And so the rate of regrowth is quite a bit higher, but then also, instead of incising a lot of the channel systems, there are a grading. And so there's not, basically what happens at, the situation now at Mt St Helens is the channel system is so deeply incised. Like if you think back to those cross sections, it's like 20 meters deep, right? So like, even if you have some trees growing on the banks, which you don't, but like, even if you did, the roots of those trees would be so minimal that it's sort of hard to conceptualize like that they would do anything, right? That it's not really like a, yeah. Okay, there's a question from Athena, and they ask, great talk, blah, blah, blah. I was wondering if you explored the role of ice dynamics in influencing the topography of the landscape after the eruption. That's a really great question. And I think, I think it's really tricky. So I guess I'm gonna, do you mean like glaciers, or do you mean like, okay, well, I'll take glaciers, for example. Ice melt. You mean in terms of like triggering these events, or like ice melt during the eruption? Yeah, I mean, I haven't really focused that much on the sort of like development that happens like immediately following the eruption or like during the eruption. But yes, ice melt is a huge consideration in terms of lahars and other downstream hazards, because often stratovolcanoes particularly, or not often, but many stratovolcanoes have ice, snow, et cetera. And so when they erupt, that is liquefied and then, can participate in and form lahars and other things that that do ultimately impact the longer term evolution of the geomorphic system, because a channel that's impacted by lahar is obviously going to then have a geomorphic recovery. So that's kind of what I've been thinking about. Though I will also say, I am interested in kind of how these processes are different in places like Kamchatka and Alaska that get most of their precipitation as snow. And I think one of the struggles, of course, is getting topography data that isn't snow covered. That's right. So you get this mountain and it's like, that looks very smooth. I think maybe it's covered in snow. Okay. Sean says,
are you planning? Yeah. Do you want me to? Are you planning to utilize your work to develop channelization hazard maps based on pre-eruptive topography?
I haven't thought about it really. That's an interesting. Yeah, that would be an interesting direction. I mean, I think that. Yeah, I haven't thought about that. But yeah, that's a good thought.
Okay. Thanks so much, Kristin. Jimmy,
Yeah,
do you want to?
Yeah, thanks so much. Yeah, let's give Kristin a round of applause for a great talk. And I guess, we'll be signing off here, but do be sure to tune in at the new year for additional talks and panels through the EPSP Connects. So thanks, Kristin. Cheers, everyone.
And thank you all for coming. Thanks.
All right. Thanks, Kristin.
Thanks, Kristin.